Good morning, children. In today's class, we are going to learn some interesting concept called mathematical induction. What do you mean by this word induce? Induction, or I can say induce. What does that mean? This word induce, suppose you are watching a cinema. If it is very good, will you keep it to yourself? No. You will call your friend and inform that the cinema is very good. You also go and watch. So you induce her. Then that friend, will she keep it to herself? No. She will tell to 2 more, then 3 more. So the data pass on. From one person, it goes on and on. So inducing, we just motivate others to do that. What does mathematical induction mean? When I say mathematical induction, the first point, whatever is the given statement, consider it as P of n. Wherever n is coming, put 1, prove the result, that is LHS equal to RHS. For example, if you have this result, we have learnt in lower class, 1 plus 2 plus 3 and so on is n into n plus 1 by 2. How to prove it? So when I have this result, what is P of 1? Take only the first element, that is 1. What is P of 1 for the RHS? Wherever n is coming, put 1. Simplify the answer. So this tells me LHS equals to RHS. So P of 1 is true. The second step, assume P of k is true. What do you mean by the word assume? Don't ask why. So without reason, without proving it, we just take it for granted. So assume P of k is true tells you wherever n is coming, just put k. It's an easy step. Proving P of 1, taking the given question as P of n, all these are simple. But you can easily score marks, a 5-mark question. So the given statement, just name it P of n. Second step, wherever n is coming, I put 1 and prove the result. Third, wherever n is coming, blindly put k, that is assumption. Fourth step, this only is little difficult. Assuming this result, wherever k is coming, put k plus 1, show LHS equal to RHS. Once I do it, see, k is true, I assume, and I showed k plus 1 is true. What does this tell me? First step, I showed 1 is true. If 1 is true, 1 plus 1, 2 is true. If 2 is true, 2 plus 1, 3 is true. If 3 is true, 3 plus 1, 4 is true, and so on. So, the induction procedure tells me, if I show P of 1 is true, assume P of k is true, prove the result for P of k plus 1 is true, I can declare the given statement P of n is true for all natural numbers. Starting from 1, I can keep on telling 1 plus 1, 2, 2 plus 1, 3, 3 plus 1, 4, and so on. So we say n belongs to capital N, or in words, all natural numbers. Let us proceed with the exercise and have these ideas in mind and prove the result. Exercise 4.4, question number 1. Prove that 1 cube plus 2 cube plus 3 cube and so on up to n cube equals n into n plus 1 by 2 the whole square by using the principle of mathematical induction. Whatever be the statement given, consider it as P of n. So the very first step, P of n be the given statement. Just copy equal plus all that, call it as P of n, so put colon. We are naming the statement. The second step, to prove that P of 1 is true. 1 tells me first term in the LHS, 1 cube. 1 cube is 1 into 1 into 1, that is 1. RHS, wherever n is coming, put 1. So this will become 1, 1 plus 1, by 2 the whole square. That is 1 plus 1 2, 2 into 1 2. 2 by 2 1 the whole square, that is 1. LHS equals to RHS implies P of 1 is true. So first step, assume the statement in the name P of n. Second step, prove that P of 1 is true. Third step, wherever n is coming, put the letter K, where K is greater than 1. So we just copy the given statement as P of K, putting n equals to K. We assume this statement. Assume tells me don't ask why. So without any reason, we just assume P of K. The very next step, I want to show P of K plus 1 is true. How to write P of K plus 1? The LHS, copy the question as it is, include one more term, that is, in the place of K, put K plus 1. K cube tells me K plus 1 the whole cube. Now use this answer. 1 cube to K cube. What is my answer? K plus 1 by 2 the whole square. Plus, what is the extra term? K plus 1 the whole cube. So let me simplify this. K square, K plus 1 the whole square by 2 square is 4 plus K plus 1 the whole cube. Taking the common term out, K plus 1 power 2 power 3, which is common, power 2. Take it out. What remains? K square by 4 plus K plus 1. How to simplify this? K plus 1 the whole square into LCM 4, K square plus 4K plus 4. What is K square plus 4K plus 4? K square plus 4K plus 4 is K plus 2 the whole square. K plus 1 the whole square into K plus 2 the whole square by 4, which is nothing but K plus 1, K plus 2 by 2 the whole square. Look at the RHS. In the place of n, I have K plus 1. N becomes K plus 1 plus 1, that is K plus 2 by 2 the whole square. So LHS equals to the RHS, and so I can say P of n is true for all natural numbers. So we'll see a quick glance of the problem. Given any question, by the principle of induction, assume the given statement as P of n. Prove the statement for P of 1. Assume, that is, wherever n comes, just put K. The next step, I want to show K plus 1. How to write K plus 1? The same K statement I write. Wherever K is coming, put K plus 1. Whole power 3 as it is here. For 1 cube to K cube, use this result. This is extra. Take LCM, common term out and simplify. Show that LHS equal to the RHS. So this answer is nothing but RHS. Because I compared. N becomes K plus 1. N becomes K plus 1 plus 1, that is K plus 2 by 2 the whole square, which tells me P of K plus 1 is true, and so P of n is true for all natural numbers. Exercise 4.4, question number 2. For n greater than or equal to 1, prove using the method of mathematical induction 1 square plus 3 square plus 5 square and so on, 2n minus 1 the whole square equals n into 2n minus 1 into 2n plus 1 by 3. Consider the given statement as P of n. The next step, I want to show P of 1 is true. For P of 1, LHS first term alone 1 square, that is 1. RHS, here wherever n is coming, put 1. 1, 2 into 1 minus 1, 2 into 1 plus 1 by 3. Simplifying that, 1, 2 minus 1 is 1, 2 plus 1 is 3 by 3. 3 cancels, again I get 1. LHS equals RHS implies P of 1 is true. The next step, assume P of K is true for K greater than 1. K equal to 1 is proved here. So we will assume K is greater than 1. Consider the given statement as it is. Wherever n is coming, we will put K. K, 2K minus 1, 2K plus 1 by 3. We just replace n by K and assume the statement is true. What is my next step? To prove that P of K plus 1 is true. Copy the same thing, 1 square, 3 square, 5 square and so on, 2K minus 1 the whole square. This is P of K. What we want is P of K plus 1. Write one more term, 2. In the place of K, put K plus 1 minus 1 the whole square. 1 square to 2K minus 1 the whole square. We can substitute this from this step. K, 2K minus 1, 2K plus 1 by 3. Plus, simplify this. 2 into K, 2 into 1. 2K plus 2 minus 1 the whole square. Or we get K, 2K minus 1, 2K plus 1 by 3 plus 2K, 2 minus 1 is 1 the whole square. Taking the common term out, we have 2K plus 1 is common. I am left with K, 2K minus 1 by 3 plus from square we have taken 2K plus 1. So what is remaining? 2K plus 1 power 1. Taking the LCM, this reduces to 2K plus 1 which is already out. K into 2K, 2K square minus K by 3. Here I have 2K plus 1 cross multiply. 3 into 2K, 6K plus 3 into 1, 3. We are left with 2K plus 1 into 2K square plus 5K plus 3 by 3. Factorize. 2K plus 1 into 2 3s are 6. We want 5. The two numbers will be 2 3s are 6, 2 plus 3, 5. By 2K, by 2K. Here I cancel. So my answer is K plus 1 into 2K plus 3 divided by 3 and this is the LHS answer. Find out what is RHS. Wherever n is coming, put K plus 1. N will become K plus 1. N will become 2 into K plus 1 minus 1. 2 into K plus 1 plus 1. The whole thing by 3. That is K plus 1 into 2K plus 2 minus 1. 2K plus 2 plus 1. The whole thing by 3. K plus 1, 2K plus 1, 2K plus 3 by 3. Compare. So comparing these two, we get the same answer. Call this as 1 and this as 2. 1 equals to 2 implies LHS equal to RHS implies P of K plus 1 is true. Since we have assumed P of K and showed that P of K plus 1 is true, we can conclude P of n is true for all natural numbers. For all natural numbers we can write n belongs to capital N by the principle of mathematical induction, and that is the answer. Exercise 4.4 question number 3. Prove that sum of the first n non-zero even numbers is n square plus n. First n numbers tells me 1, 2, 3 up to n. But now first n non-zero even numbers is the question. So 1 to n you multiply by 2 so that they will become non-zero even numbers. 2, 4, 6 up to 2n. 1 to n you multiply by 2 and the answer they have given n square plus n, sum of all. First n non-zero even numbers is n square plus n. Take the given statement as P of n. The next step, to prove that P of 1 is true. LHS only the first term, that is 2. RHS, wherever n comes put 1, it is 1 square plus 1 which is 2. LHS equals to RHS implies P of 1 is true. Assume P of k is true. Wherever n is coming, put k. And k is more than 1. K equal to 1 we have proved here. So assume k is more than 1. To prove that P of k plus 1 is true, copy the same from here. Write the next term. 2k will now become 2 into wherever k comes put k plus 1. I can use this result. 2 to 2k, I can write k square plus k plus 2 into k, 2 into 1, that is 2k plus 2, which becomes k square plus 3k plus 2. Factorize. 2, if I factorize, 1 2's are and it becomes 3. So I get k plus 1 into k plus 2. This is LHS. RHS will be n square plus n. Wherever n is coming, put k plus 1. K plus 1 the whole square plus k plus 1. N square becomes k plus 1 the whole square. N becomes k plus 1. Or this also we can take. Wherever k is coming, put k plus 1. Simplify this answer. K square plus 2k plus 1 plus k plus 1, or it becomes k square plus 3k plus 2. As I check these two, I am able to decide LHS equals to RHS. Whenever LHS is equal to RHS, I can immediately say P of k plus 1 is true, and therefore by the principle of mathematical induction, P of n is true for all natural numbers. Exercise 4.4, question number 4. Prove that for n greater than 1, 1 into 2 plus 2 into 3 plus 3 into 4 and so on up to n into n plus 1. The answer is n, n plus 1, n plus 2 by 3. Let P of n be the given statement. Copy as it is. To show that P of 1 is true, LHS, we write the first term, that is 1 into 2 which is 2. RHS, wherever n is coming we will put 1. 1 plus 1, 1 plus 2 divided by 3, that is 1 into 2 into 3 by 3 which is 2. LHS and RHS are equal, implies P of 1 is true. The next step, assume P of k is true for k greater than 1. The same statement I copy. Wherever n is coming, put k. Wherever n is coming, we have replaced k in LHS and RHS. This is true as we assume. The next step is to prove that P of k plus 1 is true. How to write it? Copy the k statement as it is. Then write next term, because now we want k plus 1. Wherever k is coming, put k plus 1. K will become k plus 1 plus 1. Now 1 into 2 up to k into k plus 1. From this step, we can write k plus 1, k plus 2, the whole thing by 3, plus Here, this can be written as k plus 1 into k plus 2. So, in both the terms, I can check k plus 1 is common. Also, k plus 2 is common. Then what is left out? K by 3 plus 1. Taking LCM, k plus 1 into k plus 2 into k plus cross multiply, it is 3. Now we get k plus 1. Check whether it is RHS. Wherever k is coming, put k plus 1. K becomes k plus 1. K plus 1 will become k plus 1 plus 1. K plus 1 plus 2. So, in RHS, wherever k is coming, we are putting k plus 1 and we check both are equal. Whenever LHS and RHS are equal, we can declare P of n is true for all natural numbers, and that is the problem. Exercise 4.4, question number 5. Using mathematical induction for n greater than or equal to 2, prove that 1 minus 1 by 2 square into 1 minus 1 by 3 square into 1 minus 1 by 4 square and so on up to 1 minus 1 by n square equals n plus 1 by 2n. The given statement we just copy and name it as P of n. The question starts from 2. So, we will start P of 2, not P of 1. P of 2 tells me LHS 1 minus 1 by 2 square. Very first term, that's all. Equals to 1 minus 1 by 4. 4 minus 1 by 4. That is 3 by 4. RHS, wherever n is coming, let us put 2. So, it becomes 2 plus 1 by 2n. 2 into 2. That is also 3 by 4. LHS and RHS are equal, implies P of 2 is true. Assume P of k is true. Now we will say k is greater than 2 because k equal to 2 we have proved the answer. So when I assume what I don't know only I can assume. So assume P of k is true where k greater than 2. Copy the same result wherever n is coming, put k. Now we want to show P of k plus 1 is true. Again copy the same. Write one more term because this is P of k. I want P of k plus 1. Wherever k is coming, write k plus 1 the whole square. Up to this term, I can substitute k plus 1 by 2k into, I can take LCM, k plus 1 the whole square, cross multiply, k plus 1 the whole square minus 1. K plus 1 square will get cancelled. How do I simplify this further? The numerator, k plus 1 the whole square, k square, 2k plus 1 minus 1 divided by 2k into k plus 1. 1 and 1 will get cancelled. We are left with k square plus 2k by 2k into k plus 1. Taking k as common, it is k plus 2 by 2k into k plus 1. K and k will get cancelled. K plus 2, I can write, look at the RHS, wherever n comes, I want k plus 1 by denominator 2 into n, I will write k plus 1. Check they are equal. K plus 1 is k plus 2. 2 into k plus 1 is here in the denominator, and this is nothing but the RHS. I started with LHS and I arrived at RHS, and now I will say LHS equals RHS implies P of k plus 1 is true, and so P of n is true for all natural numbers, In this problem, n greater than or equal to 2. Exercise 4.4, question number 6. For n greater than or equal to 2, prove that 1 by 1 plus 2 plus 1 by 1 plus 2 plus 3 plus 1 by 1 plus 2 plus 3 plus 4 and so on up to 1 by 1 plus 2 plus 3 and so on up to n equals n minus 1 by n plus 1. The question starts from n greater than or equal to 2. So, let us take the statement as p of n. Start proving p of 2. The very first term 1 by 1 plus 2, that is 1 by 3. In the RHS, wherever n is coming, put 2 because we are starting with 2. So it becomes 2 minus 1 by 2 plus 1, that is again 1 by 3. LHS equals RHS implies P of 2 is true. Assume P of k is true where k greater than 2. The same statement you can copy wherever n is coming, replace as k. The very next step, prove that P of k plus 1 is true. Copy the k statement as it is and write the next term. For writing the next term, I copy the same. We stop with k here, but in the next term, I stop with k plus 1. First k terms. From this step, I can write k minus 1 by k plus 1 plus 1 by 1 plus 2 plus 3 up to k plus 1. 1 to k plus 1. What is the formula for 1 to k plus 1? Use the formula 1 plus 2 plus 3 up to n is n into n plus 1 by 2. 1, 2, 3 up to k plus 1 is k plus 1 plus 1 by 2. By applying this formula here, we have first term k minus 1 by k plus 1. Second term, the denominator is k plus 1, k plus 2 by 2. Taking the LCM, it is k plus 1 into k plus 2. This by 2 I can put in the numerator. K plus 1 is here. What is extra? K plus 2. Cross multiply. K minus 1 into k plus 2. When I reciprocate, the 2 will go here. Simplify this answer. This is nothing but k into k square minus k plus 2k minus 2 plus 2 divided by k plus 1 into k plus 2. Again, plus 2 minus 2 will get cancelled. We are left with k square. 2k minus k is k by k plus 1 into k plus 2. This is k common into k plus 1 by k plus 1 into k plus 2. K plus 1 I can cancel. I am left with k by k plus 2. This is my LHS answer. Let us proceed with RHS. What is RHS? RHS, wherever n is coming, I have to put k plus 1. So this becomes k plus 1 minus 1 by k plus 1 plus 1, or we get k by k plus 2. Just remember, LHS we derived k by k plus 2. RHS is also k by k plus 2. So we can declare LHS equals to RHS implies P of k plus 1 is true. Therefore, by the principle of mathematical induction, P of n is true for all natural numbers, and that is a question.